Welcome everybody to the webinar of today. The speaker of today is Renzo Ricca, and he's going to talk about a topological route to superfluid turbulence. As usual, I introduce the speaker very briefly, and then I leave him the floor. So after graduating from Politecnico di Torino, Professor Ricca went to Trinity College, Cambridge, where he studied mathematics. In 1991, he was awarded of the Knight Prize while preparing his PhD. He received his PhD from Cambridge University with a dissertation entitled Geometric and Topological Aspects of Vortex Filament Motion under the supervision of Professor Moffat. In 1992, he was elected Research Fellow at the University College London, where he worked also as a lecturer. In 2004, he moved back to Italy to become Professor of Mathematical Physics at the University of Milano Bicocca. From 2016, he is a Distinguished Guest Professor at Beijing University of Technology. And from 2023, he is an affiliate member of the SKCM2 World Premier Institute of Hiroshima University. During his academic life, he visited many prestigious research centers, organizing and directing several advanced schools and conferences, including the long-term intensive research programs, such as one of the geometry and topology of fluid flows at the Newton Institute in 2000, and one of the notes and applications at the De Giorgi Mathematics Center of the Scuola Normale di Pisa in 2011. He edited 4 books and published more than 80 papers. So it's with great pleasure that I introduced Renzo Ricca for the seminar of today. So Renzo, I stop sharing my screen and you can start sharing yours.
Okay. Here we go.
So we now see your screen.
Okay.
Perfect.
Okay, so I guess I can start this lecture. And first of all, I have to thank Professor Vasilikos in particular for his very kind invitation. We were mates in Cambridge a long time ago, and then we didn't see each other for a while. And I had this opportunity this year, and I thank him very much. Of course, also Professor Romano for helping with all the technicalities. The lecture of today is focused on some work that is based on progress in applications of topological techniques. And because my audience is mainly made by fluid dynamicists, I just have to start with an apology in the sense that my physics background and my fluid mechanics background are based more on the mathematical side than physical side. And then when we go to superfluid turbulence, even more so, I'm probably a newcomer to some extent. So please do not hesitate to ask questions during the presentation, especially about mathematics. And if you have some aspects about the superfluid turbulence, then ask Marc Brachet or others, Carlo Berenghi. Okay, so the summary: quantum vortex defects and the hydrodynamic formulation is a startup. Helicity in terms of linking, writhe, and twist, just to recall some basic information. Quantized circulation and zero helicity condition is an important aspect of this. Topological scenarios in the dynamics of quantum knots, and then quantifying the topological cascade by adapted knot polynomials, which represent something new, I hope, to all of you. Decay patterns as geodesic flows, something technical in this context, and then finally maybe a view of the formation and description of turbulence in superfluids by information on optical unlinking pathways. Right, so I'll start with just a summary of kind of recent works. This is an old one that I was part of with Carlo Berenghi on analyzing by geometric and topological techniques vortex tangles in superfluid turbulence. It is 22 years ago that we published this work, and almost 24 years ago that we started working on this. And you will see at the end of my presentation that a lot of progress has been made in this direction. Well, of course, a great progress has been made in the simulations of vortex tangles in quantum turbulence. This is a simulation of 2016, and of course, even more so, probably influenced by our friendship with Carlo, the search and findings of knots and links in superfluid turbulence, which is a very striking result, not because knots and links were not popular in my mind, at least, but of the complexity of the knots and links that have been found. Of course, all these structures, or better, the geometry and topology of these structures is rather evanescent, in a sense that is heavily time dependent, so everything changes continuously as the flow develops. However, the finding of very complex knots that no knot theorist can tackle given the complexity is a kind of surprise. I remember more or less in the year 2000, Professor Moffat, we were in the conference in Japan, and he was very puzzled by my interest in applying eventually knot polynomials. And of course, he was thinking of classical fluid flows. And then there he was probably right to think that structures want to form very complex knots. You will see. Anyway, okay, so let me start with the quantum hydrodynamic formulation of condensates. As you know, Cornell, Wieman, Kettle received a Nobel Prize in physics for the first time production of condensate, and it was a remarkable result, given that some of the theory relies on the work of Bose and Einstein, so back at the beginning of or at least the 1920s, more or less. But the real production of these extremely low density and low temperature gas of boson has been achieved only in recent years. And also in recent years, Anderson and co-workers were able to detect and visualize the formation of defects in this gas. All right, I will focus in particular on these type of gas, BACs, Bose-Einstein condensates, and here I will show immediately an equation, the Gross-Pitaevsky equation, which is a mean field theory equation obtained from analyzing the quantum mechanical properties of the bosons. Here, psi is a wave function, a function of the vector position x and time t, and we assume throughout my presentation that this gas is extended to infinity. The wave function that describes the probability of particle position is assumed to be psi squared going to 1, and that as we go to infinity. As I said, this equation is the non-dimensional version of the physical equation, and so you won't see any physical terms, physical constants here, but I can, of course, give you some simple information about the physics. I can just like to tell you that we deal with a gas where the Mach number is roughly in the non-dimensional form 1 square root of 2, and the h bar over m, i.e. the Planck, the normalized Planck constant divided by the mass of the boson, is taken to be 1. All right. Back in the 20s, 1927 or 26 actually, Madelung proposed a transformation that is absolutely remarkable. He proposed to combine psi in terms of rho and theta, interpreting rho as density and psi mod psi squared as a density, and grad theta as velocity. And by doing this, so you just apply this transformation to the GPE, the Gross-Pitayevsky equation, and you separate imaginary part and real parts, and you get what is known as the two equations that give you a hydrodynamic interpretation of GPE. The first equation is obviously known to everybody, is the continuity equation. The second equation is remarkably close in form to the Navier-Stokes equation, except that the tensor part is given by gradients of the density rho rather than velocity, whereas the usual pressure term is here represented by density again. So what we have here is the information about the velocity in terms of phase of the wave function and density and gradients of density, and that's it. Right. So let me move on a little bit on the mathematical treatment of these defects. A defect, technically speaking, is, or in mathematics, is a nodal line of the wave function. Okay, so it's a line that can be seen as an intersection of infinitely many isophase surfaces. Let's call this line L, and these isophase surfaces labeled by the variable theta, and S is the surface of one of these isophase surfaces. Now, if we apply the Madelung transform, and we see immediately that because U is the grad of theta, eventually U is lying normally to any of these isophase surfaces as the nodal line moves in space, if you like, and circulation is then different from zero. We have circulation around the nodal line because of this. What is a defect? Well, actually, a defect, this is maybe the key difference with superfluid helium. A defect in condensates is actually a hole. A hole, the condensate is everywhere, and we identify this hole with a very thin hole with a nodal line, and so is a line where there is no mass, no particles at all. And because it's a hole in the fluid medium, so to speak, then we should consider proper treatment of this that is actually not yet present in books on the topic, because one thing is that we have, given the fact that circulation is different from zero, we have to consider the vorticity as a delta function, first of all. But then we have a problem with the velocity, because the velocity is grad of theta, so the curl of grad is zero, so we have to accommodate this discrepancy. And this is a little bit of work that I've done on this with collaborator. So the first thing is, remember, we have a hole in the ambient space. A hole means that makes the ambient space multiply connected. So the velocity away from the hole goes typically with 1/r behavior. The ambient space is multiply connected. Theta is multi-valued. So we have to apply multi-valued gauge theory. And this is done by using Kleiner's multi-valued approach, which I find particularly useful because it highlights the physics as well, rather than using analytical techniques typical of functional analysis. So the hole is here in front of you, and then you will see a green segment, and this green segment represents a cut, so a Riemannian cut. And then u theta, of course, is the velocity normal to this cut. So I identify the cut with one of the isophase surfaces that are foliating the ambient space. So let sigma be this cut. And then what we do is just applying Kleiner's technique. I won't show you details of this, but it's pretty straightforward. And the work in Foresti and Ricca is JFM, I believe, 2020. You will find this expression, and you will see here that there is the role of this delta function, and in u, so it's a correction to u. I apologize if you see this chi. I meant to be theta, my isophase surface. And here again, you have the curl that this time is well defined because the delta function along the nodal line finally is given by a delta function along the unit tangent, and so we can give a proper sense to the curl operator. Gamma, well, theta is multi-valued, so circulation around the defect line is gamma and has these 2 pi n values, so it's quantized. So the first news is that we have circulation quantized, but other than that, Biot-Savart applies. So you have a velocity field that obeys classical fluid mechanics properties, and more than that, you have the hydrodynamic formulation that I showed you before. And so we can take advantage of a lot of techniques that have been refined during the years in dealing with direct numerical simulations of classical fluid mechanical problems, in particular vortex dynamics. All right, so this is the entry, and then we have another entry on helicity. Well, most of you know helicity. We know that this integral, the integral of the velocity times the vorticity over the domain of vorticity, is an important invariant in ideal fluid mechanics. And we have here to recall the work of Moreau, 1961, where he proved that from Euler equations you can show that H is indeed invariant in time. And from that time, especially with the work of Keith Moffat in 1969, then helicity became more and more quantity that has been investigated, in particular in relation to energy dissipation. Okay, let's go back to the ideal case. And here we have this result that is rooted in Moffat's work at 69, where there is a relationship between topology and helicity. Well, helicity is invariant of ideal fluid mechanics. If we localize vorticity on thin tubes, in particular forming maybe knots and links, then you can prove this relationship. And this relationship is quite important because especially with the new software based on analysis of geometry and topology of localized field lines, we can compute helicity by working on the second, on the right-hand side of this equation, which is far, far more easy than the left-hand side. And the right-hand side that you see is an expression in terms of the circulations of a number of vortex filaments. And then we have these two quantities, LKIJ and SLI. A quick reminder of these quantities. LKIJ is just the Gauss linking number. And this, I remind you, can be computed by any projection from numerical data, any planar projection as the one you would see, of course, taking care of the orientation induced by vorticity on the filaments, etc., through counting the crossing. Because linking number is a topological quantity, it does not matter which projection you take. And so whatever projection you take, you get this number. And so this is a great help. The second quantity comes from a limiting form of the Gauss linking number and is called so-called self-linking number from the work of Calugarianu, 1961, and White later on. And actually, you see an R there. The R refers to the fact that we have to refer to a ribbon. A ribbon is where LILJ denotes the center line of our vortices. RI has to refer to a ribbon. The writhe and the twist decomposition of the self-linking number is an important aspect. It means that this topological quantity admits decomposition in terms of global geometric quantities. This is pretty important. And the writhe of the axis of the center line of a vortex filament is a measure of the folding of this ribbon in space. So it can be computed again by evaluating crossings. Apparent crossings is a geometric quantity, so it depends on the projections, but there are lots of tricks that you can implement in order to have only just very few projections, maybe just 3 good projections give you a good estimate of the writhing number. And then the twist. Twist depends exactly on the ribbon. And the ribbon is defined by taking the center line of a vortex and then a neighboring curve, a neighboring vortex line, so to speak. For defects, we do not have a secondary line to refer to, but we can take a secondary curve on an isophase surface, any isophase surface, to construct an artificial twist, or better, an artificial ribbon, from which we can get information on the twist. And of course, twist is a very important quantity because it contains a lot of information about energy, torsional energy that eventually gets transferred, as well as writhe helicity during reconnections. So this is the ideal setting. Now let me go to GPE. GPE is a very special kind of setting because we can prove rigorously that under Gross-Pitaevsky equation, helicity is conserved, so is constant in time, but its value is 0. And the fact that helicity is 0 was known to a number of people already in the year 2010, more or less. A number of papers came out showing that helicity is 0. And so I remember at the international conferences people coming to me and asking, what's the point to have helicity there if it is always 0? How can you pretend that is a conserved quantity if you do not see it? And any quantity that you do not see is conserved. Okay, good point. But here you will see not only that we have a proof of that fact, but the consequences of these facts are very interesting. So this fact has a corresponding topological proof when we consider a tangle of defects in space. So if we have a system of defects in space, the same proof by topological techniques is given. So the helicity reduced to linking number sums is equal to 0. You notice that I took circulation equal to 1 because defects in condensates are, how to say, stable, or better, physically realizable stably only when their circulation is 1. It's a very interesting point also from a mathematical viewpoint to understand why they cannot sustain higher charged topological charge. Anyway, okay, this is the situation. So we assume that from now on, gammas, all the circulation in our defects are equal to 1. And here we have the extension of this result, sum of Gauss linking number plus the sum of all geometric quantities, giving you self-linking to 0. Now, for a defect, it means simply that a single defect, there is no Gauss linking number, of course, and we have one quantity, that is the self-linking number, and the self-linking number setting to 0 gives you writhe plus twist equal to 0. So if there is a writhe, i.e. formation of coils, it must mean that there is a kind of torsion and the kind of rotation of isophase surfaces around the filament, the nodal line, to compensate the writhe. Even more interesting if we consider a multitude of defects. And I don't have time now to go into that. Is a separate issue and also extremely interesting from a mathematical and physical viewpoint. But I want to give you an idea of the physical implications of this. So consider 2 defects only. So you have 2 defects that are linked together. So the linking number is, for example, +1 as a Hopf link, as I show you. So we have contribution from linking number, but we have also to consider the contribution from the self-linking of each contribution. And this gives us a corollary, a single vortex defect, in this case, of self-linking different from 0 cannot exist in isolation. This means that if we produce, for example, a vortex ring, and for some reason we are able to inject externally, we are able to superpose a twist phase, then because the twist will be different from 0, then to get the sum equal to 0, that will induce something else. And not only writhe, but eventually something else. Indeed, the smooth foliation of the ambient space got broken, and we have a topological instability with production of new defects. And this has been done in a numerical exercise with Simone Zuccher. You'll see we have a single vortex ring here, and then we superpose a twist on it, and we have an instant formation of a central new defect. And so new production of new defects just from pure geometric and topological aspects. So this might be a technique that will be implemented, may well be implemented in the future to produce complexity, new defects from single vortex rings. Okay, so this is the setup, and then I want to move on to show you some results due to Simone numerical simulation. Here we have a Hopf link, and then there is a reconnection, and the reconnection with the formation of a single loop, and then, as we know, a kind of cascade to small rings. If we go to take measures of this helicity, we can show that indeed remains basically conserved and equal to 0. The black dots denote points of reconnections, and here we have the split of the contribution from total writhe and total twist that, as you see, evidently compensate one another. If we go into detail, I won't bore you with all these details, but if you go into details, you see that from the Hopf link, you see the exchange of writhe and twist. Then after the reconnection, you have first reconnection, you have formation of a single loop, and then the 2 loops, and so on and so forth. And you see for each stage that helicity remains conserved with individual exchange of writhe and twist between different structures, and eventually a formation of more and more loops as the simulation evolves. So far we saw the cascade of Hopf defects to unlinked, unknotted loops. And well, many of you will know probably the work of William Irvine and Kleckner in 2013, the production of a vortex knot in water, a remarkable result. You see here a snapshot of their movie, and at the bottom here you see the characterization in topology of these configurations. So that is a trefoil knot. So remember, topology does not care of geometric details. All right, as we follow in time, there is a production of Hopf link, and then farther down in time, the production of a unlinked, unknotted loop, single loop, and then farther down, the formation of 2 evanescent vortex ring that quickly, of course, dissipate in fluid. Remember, this is an experiment in water. The only remark I have to make on this is nothing tragic or particular, but please remember that the trefoil knot was formed by the injected so to speak, low pressure field line received from the impetus or the input of an instantaneous motion of a trefoiled shape airfoil. So the trefoil shape that you see here, the topology that you see here, is inherited from the topology of the airfoil. So the question for me was if it is possible to produce these knotted vortices exactly a la Kelvin. Kelvin imagined to make a vortex ring interacting, reconnecting, and producing knots. And indeed, it didn't succeed. And my question, even at the time when the work was done with Carlo Berenghi in 2000, was to produce a vortex knot from unlinked, unknotted loops. In other words, to reverse this pattern. All right. Well, topological scenarios in the evolution of these objects are infinitely many. Here we have Simone reproduced the head-on collision done by Nichols and Tim long time ago. That is a beautiful result published in Nature 91, I guess. And here we have our vortex rings. There are already instabilities, and the instabilities trigger the reconnection locally along these defects and the formation, abrupt formation of many ringlets. Now you see here we have what I call a topological collapse, because we do not have a single reconnection at a time, but because of the symmetry of the system, a multitude of reconnection happening instantaneously. Similarly, if we take a torus knot of higher complexity, say the 2-9, which has 9 crossings, and we look at its evolution, because of the symmetry, the mathematical prescription that gives you a very symmetric knot, then eventually you will see a collapse of this structure to a number of loops. First, something like this, and then many other ringlets. I want to show you the movie here, and you see the rotation and translation, the instantaneous production of a loop, and then the smaller loops produced. This is because is a kind of collapse, because we see many reconnections in this particular case. In the last stage, we have 11 reconnection happening at exactly the same time. Of course, when you produce these results, you can analyze in great details whatever you want. Here we have length and total curvature. Global curvature is global geometric quantity, is not a topological quantity. If you look at how curvature, the global curvature goes, you see these peaks. You can analyze these peaks, and you see different gradients or different stages to get before the reconnection and after the reconnection. Remember, these dots are just labeling the reconnections that we saw in the HOMFLYPT evolution. And helicity, HOMFLYPT, and in this case is the torus knot evolution. The same thing for helicity, for the torus knots, or for all other tested configurations. You see that helicity is exactly 0 and is compensating writhe and twist throughout. Now we can keep going, and we have also different types of topological scenarios. For example, something that goes from 3 loops, 2 loops, 1 loop, 2 loops, and then back to 3 loops, of course. And this is a kind of cyclic progress, a cyclic pattern. But I like to show you a work on the formation of a trefoil knot from the reconnection of unlinked, unknotted loops. Is a numerical work, of course, done by Simone, but I think it's pretty remarkable. What's special about this is that because you work with numerics, you can fine-tune your geometry, i.e. your initial conditions. And so you can get the right initial condition just to break up the symmetry of the system and to allow one reconnection at a time. And if you do this, you just reverse the process that you saw in William Irvine or in other works, i.e. the normal or the typical cascade of the trefoil knot. So you go from a 2 unlinked, unknotted loops to the formation of a single structure, one color, this one, the 1 loop, and then the formation of a HOMFLYPT, 2 colors, one dark blue, one light blue, and then finally the formation of the trefoil knot. Let me show you the video. Is pretty quick, but you will see 2 unknotted loop, 1 HOMFLYPT, and finally the trefoil knot. Okay, so this is quite nice. It shows very evidently and clearly how initial conditions are relevant for this. And that's why Kelvin had that difficulty to produce vortex knots, because he had to experimentally, with a setup by Tate, to shoot vortex ring to modify the aperture of the box in order to produce these vortices with a very, very specific geometry. And this is extremely difficult. In other words, I like to change my word. Extremely difficult means, to some extent in nature, unlikely, very improbable to happen. So you see, this gives me leads me to the second part of the talk. We have this sequence of defects in condensate, sequence of vortex filament in water, but even the same sequence, i.e. this topological pattern of cascade in DNA plasmids in biology, which is quite remarkable. So what this generic pattern is so special about, I don't know. So we started to investigate this with collaborators from China, in particular Xin Liu. And the typical topological cascade that I show you already a number of times is given here in terms of little drawings. And in terms of topology, you go from torus knots to torus links, and then torus knots and links, etc., until formation of simple loops, and possibly smaller in scales. Well, helicity, I told you, is not a great help for the case of condensates. Certainly helps in class, say, superfluid turbulence, like helium superfluid, etc. Because of this limitation, we have the chance to use polynomials. Now, polynomials, just trust me, are invariant quantities that detect topology. And here we have just a P of L, the polynomial of L, in two variables, A and Z. A and Z are just dummy variables, no physical meaning for knot theory, for pure knot theory. And if we want to evaluate this polynomial for a number n of rings, unknotted, unlinked loops, this is the expression we have. And of course, it decays with n, with decaying n, with increasing n. Then we have an expression, or better, two different expressions for HOMFLYPT. We have no orientation here. If we prescribe orientation, we would have a positive hop, a negative hop link, and different polynomials, of course, and so on and so forth. Trefoil knot, right and left handed, the whited link, one type, and the mirror image, Borromean rings, and you see these polynomials get very complicated. But from a topological viewpoint, the good news is that as far as as long as the crossing number is not so high, these polynomials identify very well the topology of the knot or link type uniquely. Of course, we have other polynomials, as you know, and in particular, the Jones polynomial. As you see, Jones polynomials give different polynomials, and is a polynomial in the variable t. So one single variable rather than two. Okay, so what we do is just to investigate if there is any way to derive these polynomials from fluid mechanics. And the result is the following: is a JFM paper, remarkably. The big result is not the theorem itself, is to have published this in JFM. Well, if we consider fluid knots of a given helicity appropriately rescaled, then these E to H satisfies, under plausible statistical hypothesis, the skin relation of HOMFLYPT polynomial, where A can be shown to be related to twist, and Z related to writhe. So we can have information in the polynomial. Polynomial detects topology from a qualitative point of view, but if we have some information about writhe, helicity, or twist, helicity, i.e. numbers, we can give numbers to the polynomial. So the polynomial becomes a quantitative measure of that particular topological type. Now, what happens to Jones? If we reduce HOMFLYPT to Jones, then the two variables become one. And the good news is that from the fact that writhe plus twist is equal to 0, we can rescale twist and writhe into a function t that becomes a function either of the writhe or the twist, doesn't matter. Now we care about the writhe because remember the writhe can be measured as a geometric quantity far more easily than twist. By the way, even numerically, twist is complicated to evaluate because it involves torsion aspects, and torsional contributions involve third derivatives, etc., etc. Okay, now we have unlinking paths. We saw starting from, say, something pretty complicated like the 2-6 torus knot that gets to the unlinked, or a number of loops that are unlinked and unknotted. So how many paths we can identify? Well, we have these possibility, of course, and this is what has been seen in nature. But we may have other possibilities if we allow each transition, each topological change, say from a link to a knot to a link, to occur under a single anti-parallel reconnection. Then we may have other possibilities like this one, or like this one, or like this one. So we have many different possibilities. So with Xin Liu in particular, we embarked on this work. Is an amazingly long and cumbersome work because we have to evaluate all possible transitions. Well, first of all, we could prove with Xin. Well, first of all, let me say we have this path or this alternative path. With the Xin, we proved 2016 that this path gives a monotonic decreasing sequence of numerical values for the knot polynomials, for Jones or for HOMFLYPT. And that made us believe that it was a wonderful news because we have a polynomial that detects this path in a monotonically decreasing way, and so it works perfectly well in agreement with the experimental results. But then we have other paths to consider. And other path, this is the result. We have 313 that goes to 244, 189, etc., as we go from the torus knot 2-6 to the link 2-5, 2-4, following this path. But then, if we follow this alternative path, in the later year, we discovered that also this alternative path is consistent with the monotonic decreasing sequence of numerical values. And this was a big puzzle. Why we observe only this one rather than maybe something like this or very complicated others. By the way, this type of link is a collection or a union, disjoint and then joint union of trefoil knots. Why we don't see that in nature taking place, and neither do the biologists and other people in chemistry as well. Okay, so the question was quite interesting, and now I need your patience because I will jump to a little bit of mathematics. Now, we need to introduce a new approach, and the idea was to reconsider these unlinking paths as some kind of flows in an abstract space. What about a knot polynomial space? This is something new in knot theory as well. So this is the way it goes. Well, we consider a number of knots and links, and we consider a single reconnection at a time so that we can identify well each topological configuration. We identify each type by, say, the Jones polynomial or another polynomial. For simplicity, we went on with the Jones polynomial. Now we go to the adapted version of the Jones polynomial. In other words, from the Jones polynomial, we went to this transformation e to h, so to speak, or e to Reith in that case, and then we go to the numerical value. So we have a numerical value for each topological type. Now, the numerical value that is standardly assumed in knot theory is for the unknot, and that is set to be 1. Okay, the Jones polynomial of the unknot is known to be 1. If we proceed along this way, we consider the value of the Hopf-link, the value of the trefoil knot, the value of all the knots and links that you saw in that particular diagram. And once we have these values, we can put these values in relation to one another by imagining to embed these values in a particular space, in a metric space. Imagine is like general relativity, so nothing new in a sense, except that in general relativity, the biggest mass is the mass that deforms towards the bottom your manifold, and here is the highest complex knot is standing up on a kind of mountain peak, and then you imagine that by reconnection and continuous processing of reconnections, this knot evolves through these mountain landscape to form simpler and simpler knots until it gets to the very bottom, a lot of unlinked, unknotted loops. And this is the value 1 that we take as a reference. And once we are there, we can construct or better define our knot polynomial space. So the polynomial space is defined as an n-dimensional, discrete, is made by discrete numbers, Euclidean space endowed by the metric given by, and we need the metric, so we need a distance, we need orthogonality. So we went for a family of complete polynomials of orthogonal type. So you take these polynomials from well-known PDEs or ODEs, for example, Legendre, and then these are polynomials that form a complete set, and they are also orthogonal. Oh, you make them orthogonal. And once you have this way to measure your position of your knots in space, remember each point in this space is identified by the Jones polynomial and through the adapted version by a numerical value. So once you are there, that's it. You can compute distances in this abstract space. Okay, so we go for that, and we identify possible decaying path. So we start from these knots, and you already see in transparency the path that we identified. Of course, there can be infinitely many paths, far more complex than this, if we go up instead of down in complexity, as the work of Carlo Barenghi showed. Remember, however, that these might be instances of the evolution. Okay, so if you believe that evolution anyway leads you to the formation of little loops that eventually disappear, then you identify this path and you follow this approach. Now, in doing this, you have to define certain quantities. So some quantities, one quantity is this reference distance, direct distance between the complex knot and the unknot. You take this as a reference distance, and then you compute the relative deviation of all the other paths. So we identify 17 paths. So there is a lot of basic computation to do, because you have to evaluate to sum up all the distances and to construct the relative deviation. And then you introduce, and this, of course, for all possible path you identify. So you can imagine how much work was done here. And I do believe that this will be done with artificial intelligence approach or machine learning approach in the future. So we have these paths. By the way, you notice there are arrows, dashed arrows here, because they go from a kind of privileged path line from one path line to another, or a corridor to another. And so they might have great difficulty to go in one direction like this or the other. Okay, so then we compute the probability. Probability, sum of probabilities is 1, and from each deviation you can define your the probability you like most. This is the formula we used, and then we compute the probability. So we have now an unlinking probability pattern for this evolution. Now you see, I put some arrows in light gray and the relative probability in orange, and the highest probabilities in red. So you can see very well here, at least if you trust this approach, that you have definitely information about the fact that say the transition in horizontal lines, as given here, are very improbable. And the most probable one is the one that is observed in nature. So this, I think, opens up a view of further work, and of course also of eventual possible confirmation of this approach. We don't know. I mentioned already a number of times the work of Carlo Berenghi done with his group in the first slides of finding knots and links in turbulence. They found very, very complex knots, far more complex than the pattern shown here. And there is hope in Berenghi's group. They used Alexander polynomial, which is a simpler version, but quite effective for the work done of Jones. So remember, Jones is a kind of reduction of HOMFLYPT, and you can see or interpret Alexander polynomial, one of the first, actually the first polynomial introduced in knot theory in the 1920s, as a very simple version of Jones. So why not using Alexander, repeat all these, or why not for Carlos and others not to use Jones polynomials and repeat all these? Of course, it's a lot of work for us doing manually and doing the computations. And so definitely we have kind of proof, if you like, that this sequence is the most probable one. I want to conclude my talk with drawing on an analogy. So bear with me. Also, this is a little bit off the track. We have, and we can rely on a perfect analogy between Euler flows and magnetostatic equilibria. This is very well known, at least in mathematical physics, under ideal relaxation of magnetic knots and links. We know that magnetic minima represent steady states of Euler flows. So if you are able to consider magnetic minima in terms of knots and links, then you would have information on the possible or virtual minimum energy state of a knotted configuration for Euler flows, for ideal Euler equations. Now, what I mean by ideal relaxation is just exemplified by this picture. You consider a magnetic knot and you go to the minimum energy state, and that is represented by the tight knot configuration. Similar for a link, you go to the tight link configuration. Once you are there, then you use a particular topological quantity to identify, to measure the tightness of the knot and relate this to energy. This was done also by me already almost 10 years ago, and a number of people, including Keith Moffat and collaborators, Atta Chui in particular. And you can establish a topological lower bounds to kinetic energy, not magnetic, kinetic energy given by this invariant rope length. So the rope length of each knot type at the tightest configuration is an identifier for minimum energy states. If you do this and you prescribe a complexity, or you define a complexity degree by this formula, and this is expression in terms of the Jones polynomial, you can plot these with your knot types. But of course, knot types must be identified now with rope length. And rope length is a very good identifier of the complexity of knot when and links, knots and links when they are in the tight configuration. And if you do this, you can plot chi, the complexity, not as function of the polynomial or the numerical value of the polynomial, but of the position in terms of complexity of the tight knot. If you do this, this is the expression you get. So you see several of those knots are confined in the same region, and they all can satisfy a best fit logarithmic curve. So that brings us to a conclusion. Well, there is a logarithmic there. It's interesting. And what we can say is that there is a direct relationship between the topological cascade and the minimum energy state and the associated energy erosion, because remember, all the time you go from high crossing number to a lower crossing number knot, you lose a little bit of knot length of filaments plus other aspects. And this is also related to the energy cascade. So I stop here with this question mark. Is any of these useful to have a topological route to turbulence and energy dissipation? That's all. I don't know. Thank you very much. Thank you.
So thank you very much, Renzo, for the very interesting talk. So I would say we can open the stage for questions if you agree.
Absolutely, yes.
So whoever would like to ask a question, just feel free to unmute your mic and ask the question. Or you can write in the chat and I can report it.
Can I quickly ask a question?
Yeah, go ahead, Christoph.
So hello, Renzo. It's good to see you for a long time.
Good to see you. Hi.
Thanks for giving the talk. Very interesting.
Thank you.
Very impressed by how far you've gone after so many years on this. You didn't say very much about the connections. The differential equations with which you started seem to be time reversible, I think, or not. I think
that's right. It's time reversible.
But you all these reconnections. I know this being discussed by the community. Perhaps you can say something about the connections and what you did in your simulations about it and so forth.
Yes, this is a question that, at least as far as I'm concerned, has been around for some time. I use the past tense because if you go, so the equation itself is like that. Remember, it's a mean field equation, so it cannot be exact. And when you talk about reconnection, immediately you have in front of you these two statements. One is a very local event, and the other you deal with a mean field equation. Mean field equation cannot take care of these local events, and so the discussion I heard around a number of years, I think is ill-posed. So the reconnection has to be tackled in the context of condensates by a different approach. It cannot be solved by Gross-Pitayevsky. However, how I showed there are, how to say, ways to grasp irreversibility, not more than that, and is to be very careful on the before and after time. This has been done by a number of people, Villeroy, Proment, Krustolovic, and of course many others. And And this is, for example, to detect the change in the rate of change in curvature, and the peaks in curvature and the time reversibility comes from there. You can measure the, so suppose you prescribe a time window center on the reconnection event, then you can see very well that these rate changes are different from before and after. So that's my way to detect irreversibility. You want to be able to detect irreversibility from a mean field equation. No way.
Oh, thank you very much. That was very useful answer. I see Carlo is probably going to ask a question, so I will very quickly. In the simulations you showed us, what did you do for the reconnections? You had some simulations where some vortices were going from 3 or 4 knots to less knots and so forth.
Yes. So first of all, when you show something, people in the audience are far more equipped, better equipped than me with all their skills. You always try to show what you want to show. And so first of all, defects, one way to show these defects is to emphasize the tube that you see, to visualize a tube on the nodal line. In our simulations, that was set not for the visualization. For the simulation was set to 1/100th of the density. The simulations show 1/10 of the density, so the tubes are much bigger, and the density, of course, gets to 1 as we leave the nodal line. Typical healing length is a measure of this thickness of the defect, if you like. So that was the way to visualize these things. So we kept track as long as we were in the region of 100s, and of course Simone was skilled to increase grid points all appropriately all around the reconnections. So it's a little bit of work, as everybody knows in the audience. You have to adjust the grid to the local time, space frame that you like, and then redo your computation at the higher grid points. That was done.
Thank you very much, Carlo. I think not Carlo, Renzo. Carlo has a question, so I'll let him ask a question.
Hello, Carlo.
Hello, Renzo. Thank you for the nice talk.
Yeah, thank you. Good to see you.
Just a question. Is there any experiment or evidence about the effects of thermal noise on this topological cascade?
Yes, I like to follow up your interest on this. At the moment, I cannot say anything really that makes sense, other than we like to follow much more closely the amount of energy that goes into sound and thermal aspects as well. So I cannot say anything really. I'm sorry about that. We just launched some work in this direction, considering again very simple scenarios, far from complex knots, and to understand if there is any information about that. Actually, you are the person who can tell us or update us on this. For example, the typical question: how much of kinetic and mechanical energy and thermal energy or sound emission goes after reconnection? So all these things. Yeah, I don't know. I'm sorry. Maybe you like to comment on this.
I do not know the answer.
Okay. Thank you.
Okay, thank you. Let's see if there is someone else in the audience who would like to ask a question. So just once again, feel free to unmute your mic or to write in the chat, and I can report the question. Yeah, then maybe I can ask myself one. Sure. I can ask myself a question then. So you showed before that to kind of produce different scenarios in your simulations, you do control the initial conditions such that you drive a certain the occurrence of a certain scenario. Now, what happens? What do you expect it would happen if you shrink your domain and make it periodic? In the sense, if you put several nodes which have the same dynamics close to each other, do you expect that the route to superfluid turbulence you just presented as the most probable one keeps being the most probable one?
Well, this is okay. So first of all, the one important fact, as is known, is to stay away from, as far as possible, from say your phenomenon, for example, reconnection and vortex knots interacting, etc. That's why Simone very cleverly with Cagliari, they have a number of papers there, they use the arctan map to map infinite domain to one to a finite domain, avoiding periodic conditions. That is an important thing. Second thing that you learn by using a finite domain is that if you are too close to your phenomenon, then these waves are bound to be reflected back. So once you trigger, for example, any evolution really, but say in particular a reconnection, then there is a like of a wave that is immediately transmitted in the ambient space, in the numerical domain as well, and this wave has reacts with its own phenomenon. So you want to stay away from boundaries. However, I can go in another direction, which is also very interesting. I think Carlo did some work on that too, in another context, but certainly very, very interesting for biologists. Suppose you have a kind of a finite domain given by some solid boundary, and then we know there is a kind of again probabilistic, probably law of nature that enforces topology. So you get more complicated knots given by the solid boundary. And this is just due to the interaction with the solid boundary, reflections, etc., etc. So it's like an engine. The solid boundary is provoking more complexity. And that is a way, if you like, to study these systems. Well, for biology, you understand the importance. They've been found DNA is highly knotted in bacteriophage phases, and this is because they are confined in the capsule, in the head of the phage. So yes, the effects of the boundary are, of course, very important. And for the work we did, in particular, it was important for me, for us, stay away from these effects as far as possible.
Okay. Thank you for the very clear answer. Okay, so we can ask once again the audience. Is there someone else who would like to ask a question? Or once again, just feel free to unmute your mic if you have a question, or you can write in the chat and I can report it. That doesn't seem to be the case. So Renzo, once again for the very interesting talk, and as you could see, it's kind of developed a lot of interesting debates after that. So thank you once again for the seminar, and I invite our audience to thank our speaker of today.
Oh, well, thank you very much, Francesco, and thank you to everybody, Carlos, Christos, and all the present. Thank you very much. Thank you.
Thank you, Renzo. Thank you.
Thank you. Good evening to everyone.
Bye-bye.
Bye.